Welcome again to MLCon. Glad that you are all here. Fun fact, Bashte had to change the title of his slide in the last minute because he made the last slide to introduce me. And of course he wrote, "Attention is all you need," because it's so baked into our minds that this is the one and all tool to go. And frankly, I tried to help with organizing the conference, selecting talks and everything, and we noticed that we're getting more and more LLM talks, hardly surprising, but at some point it was overwhelming. Not that we don't welcome those talks, they are great, I have given them myself, but at some point we noticed maybe we should do something else. Quick intro, my name is Christoph Henkelmann, I got an AI company, surprise, surprise. I've been doing deep learning for a few years now, and because I worked with so many different customers on so many different projects, I had to look into all kinds of different systems. That's what you do when you customer-driven business. And this is why I had to keep track of all kinds of stuff. And I have to have a very heavy information diet. And as much as I love attention and LLMs, and I have trained them when they were still manageably small myself, and I truly love them, at some point I was getting a bit annoyed with the current storytelling that everything AI equals Gen AI equals LLM, right? So problem solved, AGI coming around soon. As you will, when you talk to multiple people who really know the stuff and don't have to get billions in funding, you will notice that most people agree AGI is not around the corner. So let's cool down a bit. What I love to do in those moments, remind myself of the textbook I used in uni to learn AI with, which is Artificial Intelligence: A Modern Approach. I can only recommend it if you want a full view of what AI truly is. And of course, it starts with an attempt to define AI, and it comes up with this matrix, which I quite like. So, because there are conflicting versions of what AI should be. And the most obvious one is a system that thinks like a human, right? If we can completely replicate human thinking, I think we'd all agree that this is AI. But if you're a business person, you don't care how it thinks. You want it to work, so you want it to act like a human, which is a great achievement. However, if you build a self-driving car, you wouldn't want it to act like a human, right? We don't want Teslas to act like Elon Musk. I think we can all agree on that. So we want it to act rationally, etc. So we see that what is probably AI is a much wider field, and we have had AI systems for a long time. We just get tired of it and don't call them anymore. So, and if you look at the whole field of AI that is out there, we see that the LLMs, which are all almost exclusively, for a few exceptions, are GPT-based systems, that this is only a very tiny part of AI. And isn't it a pity that we're starting to ignore everything else? Because A, it's very interesting, which is in and of itself a good reason to follow those things and look into them, but maybe we are missing really useful solutions out there. So how did we get there, right? How is it that Gen AI, is AGI, is solving all the problems? Well, when I was in uni and read my favorite textbook, I had one lecture on neural networks, and the summary was, they are totally cool, everybody loves them, but they don't work, so we don't cover them. In 2012 that changed, and suddenly neural networks were so hot after the AlexNet moment. Everybody wanted to do deep learning. We stopped calling them neural networks, we started calling it deep learning. And in 2017, we had another smaller revolution. At first, it seemed small, but it was bigger than anybody anticipated it. We learned that attention was suddenly all we needed. And this led us to abandon our former heroes. We stopped using LSTMs, we stopped using about everything else. And very soon, we stopped even using many types of transformer networks when we abandoned BERT, good old BERT, for stories about unicorns created by GPT-2. Fast forward a few years, and all we need is a few GPUs to solve all problems of the world, and suddenly everybody is an AI expert. I should stop reading so much LinkedIn. Yeah. So, how is the current situation? I love this tweet. Can you tweet X, I don't know, about a real world use case of someone using Gen AI. So, yeah, the KPIs of the analysis were a bit off, and this person had the bright idea to ask, did you actually read the CSV? And nope, caught me there. I made up those numbers. So obviously, we should look into other solutions for AI as well. So this is not AGI soon. So what I did is I wanted for this talk to give a little overview, and I started digging what is out there. As I said, I have a very intense information diet, so of course I started off with my papers and wanted a bit to start with an overview and see where we are with transformers and LLMs, and it quickly got out of hand. I created this graphic, ironically using an LLM, I will admit that, and with some of my own intuition and what I know, and with a bit help of the LLM, I tried to make a map of AI systems out there. This is probably only 10%. I bet each of you will find one area of AI application that's not on here, and I apologize, but I had to stop at some point. Anyway, sorry, I marked in red everything that is basically dominated by LLMs. So frankly, natural language processing, there's hardly anything that is still done with the non-LLMs, but which I find very interesting and very ironic. Tomorrow at 9, we will have a talk of someone who built an NLP pipeline that actually beats LLMs for a very specific use case. And they actually, Johanna here, will actually show you how to build an OCR system without vision LLM, which is something that even I normally wouldn't recommend to my customers to do. But sometimes it's the right thing to do, and even better. So that's very interesting. You might check out this talk. So, but you see that there's a whole world of AI applications out there, and only the reddish parts are the ones where the LLMs really rule. What about the yellow parts? They are the ones where attention-based, transformer-based networks rule. And I have to admit, once I started coloring, I noticed they are getting more and more. So there's a lot you can do with transformers out there, but you will also notice there's a lot of black spots on the map where there's other systems that are state-of-the-art, where you don't use transformers. Some of you will disagree. Everybody will find one area where they disagree, and please feel free to tell me afterwards, but yeah, there's only so much time. This is only an approximation, okay? But it should give you a gut feeling how things stand. However, researching that, I think there's hardly any area left. Some of you will say table-based data, but I have an argument for that, which are not dominated by deep learning. So the good old-school machine learning algorithms are dying out. Sometimes you find an XGBoost-based application, but they're getting rarer and rarer. So right now, deep learning really rules. I'd say 90–95%, even more. But there's other stuff than attention, and definitely a lot of systems and a lot of problems you cannot solve with LLMs. So after this, of course, normally you want your storytelling, you search for arguments that support your assumptions. We are all like that, we are only human. But I had to update the title slide. So what we actually have to say is, attention is not all you need, but it is pretty useful. And you definitely need deep learning. So with that in mind, let's move on. I brought with me an example of papers that I found very intriguing in the last 12 to 24 months. There are about 500 papers that should have been mentioned here that are not there. So this is a very subjective selection, but only to give you an idea where to look and what else to do instead of just using an LLM. Something I really liked was TAP-PFN, and I have a talk called Attention is Not All You Need, and my first example is a transformer. I add the architecture that the paper is based on at the top right to give you a little idea. But this is very interesting because table-based data, basically everything you have in an Excel sheet, is something where you did not use deep learning until recently. And you can still get great results with other stuff than deep learning. But this paper is actually a transformer architecture, and it is pre-trained. And this is very interesting. It's a foundation model, but a foundation model that understands spreadsheet data and creates classifications from it, which is very interesting. And if you know what a decision boundary are, you see that the one on the right is really nice. So this is a really nice decision boundary compared to the one of typical other algorithms you might use in such a scenario. And another area where classical machine learning used to dominate is time series. except for LSTMs. But most people I spoke to who worked with real-world time series data, they all arrive at a classical ML solution, mostly XGBoost based. And so this paper is really interesting. It's called T-Rex. And I love my dinosaurs, as some people will tell you. It's zero-shot forecasting. It's the same principle. So you have a foundation model trained on a lot of time series data, but it's not an LLM. It's not a LLM-based foundation model. It's an XLSTM. So here we see for the first time LSTMs making a comeback. You will hear, I think, a lot more about XLSTMs. They are competing architecture to GPT. They are not necessarily attention-based, and they are really good with time series data. So this actually makes great predictions, and as you do in a paper, you always diss the competition a bit. You immediately see here that there's TAP PFM, you remember from the previous slides. So someone turned this into a system for time series data. And of course, then they come along with XLSTMs and say, well, we do it even better. And there's Chronos, which is by Amazon, which is also a time series prediction method. And they are better than them, of course. That's what you do in all your new papers, right? You have to show how you're better than the competition. And this is XLSTM based. And it's really useful because it is pre-trained. So if you do time series data analysis, you should look at this. Of course, the Chronos team couldn't let that stand, so they came back with Chronos 2. And they have a nice matrix where they show who they beat. And of course, they beat T-Rex. They had to, right? Chronos 2 is interesting because it is multivariate prediction. Normally in time series algorithms, you only get one prediction, one timeline that you predict, but they can predict multiple time series at once that can have correlations and causations, and which should improve the results. So this one, again, is a transformer, but not an LLM. And very interesting, it's an encoder only. So for a change, we don't have a token prediction, but we have an encoder like BERT. So it's like a battle, okay? XLSTM says I'm better. No, I'm better, I'm a transformer. So where does it go? Then you have and they use an encoder. And now along comes sundial. So this is more like an LLM, but not an LLM. It's a decoder only. That is a token prediction transformer. And this works a bit like GPT for time series data. And I put it in here to tell you, I am willing to admit a mistake. So GPTs can be useful here, but also B, because they make two very interesting new concepts that make this work. So that you can actually create a model that talks the language of time series. They have this very interesting loss through time, which makes this time series learning possible. And they have a very interesting way in which they create the tokens of the time series, because you don't have language tokens, obviously. Now you have time series data tokens. So this is also an interesting technique. But it also shows you one thing. Transformers and decoders especially are not the only way to do it. So we have three competing architectures, all claiming to be the best. Probably in your use case, you have to try them all out, and they all work, right? So we shouldn't focus on a single method. Next thing is, if you have time series, sometimes you don't want to predict anything, you simply want to find out if something is wrong, which is called anomaly detection. And here we have a very interesting paper, again now with XLSTMs. It's XLSTM-AD, which is simply stands for anomaly detection. And you will see something interesting here as well. The older ones of you who read the Vaswani paper will recognize it's an encoder-decoder. So this actually works like the Vaswani encoder-decoder, which in and of itself wasn't a new invention. Encoder-decoder architectures existed before that. But this goes back to the encoder-decoder principle. And very interestingly, it has two ways to do anomaly detection. One is by simply predicting the next token and see if the prediction is close enough. And the other one, which I really like, is it uses its internal hidden states and tries to use the hidden state to reconstruct the input, which is a typical autoencoder paradigm. So this is very interesting, shows you that you can do very different things, and it's the system, the network architecture principle, which we have used very often. Encoder, decoder, but you don't need attention to do or dot product attention transformer to build an encoder-decoder. Next up is one of my favorites, because now let's move to images and video, spatial data. I called it in the organization. And for a change, we have a good old CNN, a convolutional neural network. Transformers have taken over the area of vision lately with vision transformers, SWIN transformers. And they used to get the state-of-the-art results, because you could throw insane amounts of data at them and they would scale, 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 whereas CNNs normally are in practice more useful for normal people like us who don't have terabytes or petabytes or whatever of image data. However, the cool thing about ConfNext V2, and I can only recommend this, that you can do unsupervised pre-training. CNNs are normally more useful in practice because you can use them for a whole lot of tasks once you have a working CNN, but you couldn't reliably train them in an unsupervised way. And this paper is so interesting because it takes what we have learned about transformers, vision transformers especially, applies it to a CNN, and you get basically the same results or even better results. It's a paper. Of course, the ConfNext bubble is higher than the other one. It always has to be the best model in a new paper, right? But it is now competitive with transformers, which begs the question, if we had kept with CNNs and wouldn't have switched to vision transformers and just had put all the energy in CNNs, where would we be? So it shows you that it is not the case. I mean, transformers are great, but you can achieve it with other architectures if you apply the lessons learned. I also have a talk on that architecture on ConfNext V1 today for those who are interested. Next thing, which is really, really interesting, is Dino V3. So you should definitely know about Dino V3 if you do anything with images. It's by, I don't know, Facebook AI, Meta AI, how they call it these days, but it's the Yann LeCun lab. Well, formerly Yann LeCun lab. And they came up with Dino V3. And Dino V3 is great because it's a pre-trained family of vision models. So if you have to solve any vision task, object detection, classification, whatever, segmentation, you can use Dino or Dino and train it for your own tasks. And then again, here we saw that the same lab said we achieve state-of-the-art with ConfNext, which is a CNN. Well, now out of the same lab comes a new state-of-the-art, and now again it's a vision transformer. So it is trained with an attention mechanism. But the interesting thing is that they have distillations into other architectures. The vision transformer is great for training, but it's hard to apply it to a segmentation task, for example. You can do that, but it's not so great. And they have a distillation, so they train a vision transformer, and then they distill that learned model into a ConfNext model, and now you have a CNN again. So that's also very interesting. So if you need a great CNN, don't stop looking when you get to Dino. There is a CNN version of Dino as well. And now here's one that I really like, because in a former project I failed to solve, to implement a good optical flow system, because it's a very hard task. And it's called AllTracker. AllTracker solves the problem of optical flow, which is when you have a sequence of images and you say mark an eye or an object, you want to follow it through the this is tracking, you want to track the pixel, right? You want to follow an object and know where it is. And you also want to know where there's movement on the image and in which direction the movement is. And this thing is so great because it's a combination of a CNN, ConfNext, with a transformer, with an RNN, recurrent neural network. And what's even cooler, I think the model, it's somewhere around 100, 150 megabytes and works in real time. So if you have anything to do in that area, I really recommend you check out this model. And again, you see it's all possible without an LLM. So I got to speed up. I have too many papers picked out because they're all so great. This is really interesting because it is again, a vision transformer, so we have an image task, not with a CNN, again with a vision transformer, but this does something very interesting. They train a big model, and the question is, you don't always want the biggest model possible, right? You have compute constraints and might even not be the best. So what it does is NAS, a neural architecture search, which is, you can simply have, if you have many hyperparameters, number of layers, embedding dimension, etc., you can train a model hundreds of times and pick out the best configuration for you. However, this is crazy expensive, so you rarely do it with deep learning, right? You could do this with the old machine learning algorithms where one training took a minute or two. You could run it all night and get the best parameterization. You can't do it here. What they do is they train one huge system and they simply cut and rearrange it to get the best architecture, and it seems to work really, really well. So that way they can try a lot of hyperparameterizations, but they don't have to retrain the model all the time. I think this is a great idea. And this is one where I say, well, I learned a bitter lesson here. I really wanted to put image generation in here for you to say, what? But that's Gen AI. That's an LLM, right? Well, the first ones, the stable diffusion stuff, was built on CNNs. They had transformer parts in there, clip, etc., to get the embeddings. But the image generation was actually a CNN type called UNet. So I said, well, I'm extra smart here. I surprise you all with the fact that this is actually a CNN application. Turns out they switched to transformers, and Flux is actually built on something called a rectified flow transformers. So yeah, not so smart after all, me. But I thought I'd put it in there to show you how quickly this stuff's changed. And this is one that I absolutely like because I like vector graphics. And you cannot make good vector graphics with LLM. They can output SVG because SVG is text, but it's not really nice, right? But they can create vector-style images, but they are pixel images. We want sensible, editable SVGs. And all solutions that create SVG graphics normally create these machine SVGs, which, you know, as a designer, when you want to work with it, you want to move the head and have actually access to the parts of the image. This thing, it's pure brilliance. First of all, the technology, it's an MLP. So I don't know if any of you thought that you would find a very old-school multi-layer perceptron in this. So, and it uses stable diffusion and a LoRa. So what they did, they used stable diffusion, trained it to generate vector graphic-like images, and then they trained the MLP to recreate the SVG for that based on the prompt. And they get an image which you can prompt, and you get an SVG. So this is a wonderful paper because it shows you how you put all these things together, and it's a really tough problem. I would never thought that you could solve it like this. Yeah, there are applied domains, very special domains where you need a lot of knowledge, and you also definitely shouldn't solve ECGs, which electroencephalography, I don't know how you pronounce in English, measuring the heart rate and the heart rhythm. Don't ask ChatGPT to analyze this, please. But if you have this system, which is an XLSTM combined with SimDino, again, this combination. So this, you have a Dino V2, which is the predecessor of Dino V3, combined with an XLSTM, and suddenly you get a very good specialized system for working with this kind of data. So in these individual domains, you find interesting stuff. And don't forget AlphaZero. Everybody says, well, that was the big breakthrough of deep learning, which is true. It's amazing. Go watch the Netflix movie AlphaGo. You really have to watch it if you haven't done it. Please remember that we beat Go with neural networks and search, which is 60s, 70s, 80s AI. AlphaZero and AlphaGo work with a Monte Carlo tree search. So this is old school AI, old school search. It's not just neural networks. So still useful, and I bet you couldn't do it with only neural networks. Okay, new thing that comes up are world models. World models try to really have an understanding, a model of the world. We saw in the intro by Sebastian and Peter that LLMs are really bad at having a mental model of things because they just predict tokens. And this is a problem world models try to solve by basically creating an embedding, a mental model based on embedding of how the world works. So they don't work on a probabilistic token level, they work on an embedding level and try to predict how the world will change if certain things happen. Very important for robotics. But this really important paper, Dino world model. So they took what they learned with Dino, with the vision task, and turned that into a world model, also based in transformers, but not an LLM. It's really hard to actually just have an LLM predict the world correctly. That's what I thought until I found this paper. And I want to end with this, because I want to say, well, world models, you need something else. Turns out, actually, there's a LLM called MolMo-Act, and it's a really good world model, and it's completely open source. And how they do it is really interesting, but we don't have the time. But I wanted to end with something that I thought that LLMs definitely couldn't solve. But yeah, it's a multimodal LLM and seems to be really good. So always double check your assumptions. So we have some more minutes left. With this begs the question, what is next, right? So deep learning and transformers and LLMs obviously work. So it would be stupid to say this is useless, this is just a trick, it doesn't have applications. The reality is just too obvious. And as I said, you shouldn't always rule out LLMs, so because they sometimes surprise you. So there seems to be some more potential there. But all these systems are crazy inefficient. They need so much more data than humans to learn their task, and so much more energy, actually. We are highly energy efficient. Well, maybe not me, but others might be. So the question now is, do we stick with deep learning or not? Or do we move on? Or as we've seen with AlphaGo, sometimes it makes sense to move back. Look at the stuff we tried some decades ago. Maybe with the technology we have now, we can do better. One example I always give for the current limitations and what is hard used to be the ARC AGI challenge. So if you remove the 45.1% there, this used to be my slide to show you how hard these tasks are still to solve. But Gemini actually bumped the result on the ARC AGI challenge, which is a challenge of visual puzzles, which are relatively easy for humans, but really, really hard for AI. It bumped it to 45.1%. And this is where all the people thought, well, we probably need something else than LLMs. Well, turns out it works really, really well. So again, do we need something else, or are we on the right track? This is a pretty impressive result. However, one paper I can really urge you to read is Less is More, Recursive Reasoning with Tiny Networks. I ate this paper up. It's wonderfully written, very well understandable. And this one solved the ARC AGI2 challenge with 8%, you'd say, well, Gemini does 45.1. What do we care about 8? Remember, we were at 4, and this is OpenAI trying it. So when this came out, OpenAI threw their best models in it, and they achieved 4%. Along comes this paper this year, achieves 8% with 2 layers and 7 million, not billion, 7 million parameters, which is really, really impressive. And on ARC AGI1, which is the previous task, it achieves 40%, which is better than GPT-5 medium. Not better than GPT-5 in the full version, but 7 million parameter model being better than GPT-5 medium, I think that's very impressive. But it's still deep learning. But it uses neural networks in a very funny way that is actually not new, but nobody has done in years, which is a recursive model. Actually it's a recursive model, not a recurrent one. Another very interesting paper you might want to look into is Hill space is all you need. We all tell you in our talks, yesterday I did this, large language models cannot count, they cannot do math, which is true, but which is also funny because they are stuffed full of math. So it's linear layers one after another, and you can approximate any math functions. Everything is there in the model, but it doesn't use it in a way you would think. And Hill space is all you need is a very little paper with a very neat website that shows you with a different activation function and some little tricks, you can make a neural network learn all kinds of math functions really, really quickly. The problem is you need to know in advance which it should learn. So, but it's a very interesting idea. So this is something that in that way isn't done anymore. What I really find interesting is differentiable logic cellular automata. This is a completely weird way. It's still a kind of training, so it's deep learning-ish, but it's a way to learn logic functions. So what does this mean now? It creates a network of logical functions, which basically you can learn any Turing machine. But this is a kind of discrete system that comes out of it. So it's not some approved embeddings that are get interpolated and something is generated. So you actually learn a function, a deterministic function, a step-by-step function, which is a total different way to do things. And I think this kind of stuff is, for example, able to look at Game of Life, if you know it. It's a very interesting algorithm to simulate cells, and it can look at Game of Life. There are is an infinite variant of Game of Life. You can change the rules, and it can learn the rules of the current Game of Life in very few steps, like a few dozen steps combined to millions of steps. You would need to learn this with deep learning. So it's a completely different kind of learning things. No practical applications yet, but because it's only toy problems it solves, but because it solves very different toy problems than deep learning normally can, this is, I think, a very interesting approach, and I will show you in 2 slides why I think so. And of course, when I was in uni, back then, in the olden days, one of the things I really learned a lot about was evolutionary algorithms. They are great, they are totally fun. And this is from 1994, a great SIGGRAPH paper where the authors learned to evaluate artificial creatures that learn to walk by themselves. No deep learning, there are no LLMs, just evolutionary algorithms. And we haven't looked at them for years, and this is why I found this neural architecture search that I showed you a few slides back, where they just searched architectures to find the best match. Very interesting, because this is a similar approach to what we do here. So maybe we need to combine learning or training methods to arrive where we are. And what this boils down to is the question. These are 2 very important scientists, Shannon and Kolmogorov. Shannon you will know for information theory, and everything we do now in deep learning is in the mindset of information theory. We compress information. We think in logics. It's an information theory-based approach. It's not, you can't exactly deduce it from the formulas in all cases, but it's the mindset, right? We have gradients and we try to push energy levels down. And this is not like a battle or something that they hated each other. It's just 2 different ways of thinking about things. And Shannon is brilliant, and it's all brilliant, great stuff that works great. So I'm not saying that. But there's also the line of thinking along Kolmogorov, which deals with algorithmic complexity. That is, we want to reduce the complexity of something we have and have the discrete steps to arrive at a solution. Right now we don't get discrete steps. We get these deep learning layers, black boxes. And this is something, in a Kolmogorov way of thinking, is something that happens here and maybe here. So maybe the really, really new innovation will come from a completely new mindset. Thank you. Don't forget to vote.
Thank you so much, Christoph, and thank you so much for reading so many papers. How many papers are you reading per week or per month?
You can read papers on very many levels. You skim through the abstract, then you skim through it. Only a few I read, which means multiple hours actually going through them. Yeah. So many of them I just say, oh, this is so cool. Okay. So sometimes reading means only 15 to 30 minutes.
Yeah.
So
cool. But it's always important to broaden the perspective, right, and to understand that there are many, many more things than just GenAI, although GenAI is the main driver these days, right?
And it works. It works. If it works for you, yes, use it. Doesn't mean you shouldn't use it.
Thank you very much, and enjoy the conference. Do not forget to rate the sessions, and see you later after lunchtime for the next keynote right here on the stage. Meanwhile, go to the sessions, go to the coffee breaks, go to the booth in the expo over there, and enjoy your conference. Thank you so much.